Alright gang, here we go. So this is Chem 1, Unit 2, Part 1. Okay, and so this video is about atomic structure. We're going to talk about subatomic particles, beginning ideas of what the atom looked like. We're going to talk about abundance, isotopes, and calculating average atomic mass. So it's a pretty dense unit. Alright, so here we go. Alright, so here is what we call the Bohr atomic model of a nitrogen atom, alright, or the Bohr atomic model. This is the important part, the Bohr atomic model. Now this is essentially what most people think of when they think of an atom, and we'll talk about the shortcomings of this model coming up in a couple of videos. But ideally, in essence, we have the protons and neutrons, and they're all situated in the nucleus, okay, so right here in the middle, a big old dense middle part, and then we have the electrons on the outside, okay, and notice how, according to the Bohr model, the electrons here are at specific levels, almost like planets orbiting the sun. It's kind of the basic idea of this model. And we'll talk about how this doesn't actually work or doesn't match observations we make about electrons, but the protons and neutrons really do exist in the middle of the atom, okay? So here is our job of subatomic particles, all right? So the protons identify what the element is, okay? Yeah, all right, they're also positively charged, okay? All right, and they reside in the nucleus, okay? So the proton, we use this to actually tell us what the element is. Okay, hydrogen has 1 proton, helium has 2 protons, lithium has 3 protons, etc., etc. Okay, and then electrons are what allow us to participate in bonding. So this is what connects one element to the next. Connects elements together. All right. Now these are so they participate in bonded. They're negatively charged. Okay, so they're the opposite of protons. Okay, and they are outside the nucleus. Okay, for the sake of shorthand, a lot of times you'll see electrons represented as an E with like a negative sign up in the superscript, and protons will be like a P, lowercase p, with a positive in the superscript. All right, and the neutrons are neutrally charged. Neutrons, neutral, so they don't have a charge at all, and they also exist in the nucleus. All right, they are there in the nucleus, and you can kind of almost think of them as the glue that holds the nucleus together. Now that idea is a little bit of a sneezing tree, but that's okay. All right, so they keep the nucleus together. All right, so 2 terms you need to know: the atomic number, okay, and this is defined as the number of protons. Remember, protons are P+, okay. Now, this is the order on the periodic table. So you notice that if you have your periodic table handy, or pause the video and Google it real quick, pull one up, and you'll see that in the top left-hand corner, or maybe top in the middle, depending on what periodic table you're looking at, the number is increasing across rows, right? You go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then the next row 11, 12. Okay, those are the number of protons. So hydrogen has 1, right below it lithium has 3, etc., etc. Okay, and so they're listed by atomic number. In a neutral atom, so in a neutral atom, meaning an atom that has no general positive or negative, okay, the number of protons of an atom equals the number of electrons. So protons and electrons equal each other. So here coming up, we're going to ask ourselves questions like how many protons, how many neutrons, how many electrons does it have? Okay, the atomic number tells us how many protons it has, so we just have to find it on the periodic table and find its number, and then that's the number of protons, and then the electrons automatically equal that number. All right, mass number is equal to the number of protons plus the number of neutrons. Now the idea behind this is that protons and neutrons are very heavy. Okay, protons and neutrons are very heavy. Okay, so they determine the mass. Electrons are so tiny and so have such less mass than protons and neutrons that essentially they're negligible when we're talking about the proton or the mass of the element itself. Okay, so the mass number is what we use to determine the mass of the element, and it is the number of protons and the number of neutrons. Okay, so instead of writing all this stuff out, there's 2 shorthand notations for an atom. there's one that looks like this, okay? The A, all right, A is the element symbol, okay? Element symbol. If I could spell, that'd be awesome. Symbol. All right. The X is the mass number. Now remember, mass number is protons plus neutrons. Okay. And the atomic number is the number of protons. Okay. And so here in this shorthand notation, this X would tell us the mass number. All right. And this Y tells us the atomic number. Or essentially, it tells us the number of protons. Okay. In this other shorthand notation, notice that they totally skip out on giving us the atomic number, and they only give us the mass number. And here in a slide, we'll talk about why that would be the case. All right. So down here we've got two examples, and we want to say how many protons, neutrons, and electrons are in this element. All right. So Au, you should all know now that Au is gold. All right. So we can find gold on the periodic table, or Au. All right, now, so the number of protons, well, the number of protons is equal to the atomic number, and since we're in this shorthand notation, we know we're going to use this guy up here. All right, the Y value here is 79, and that is our atomic number, so the number of protons is simply equal to 79. We also know that the number of protons and the number of electrons have to equal each other, so that also has to be 79. All right, neutrons require a little bit of math. We know that the mass number is equal to the number of protons plus the number of neutrons. So what we need to do to find the number of neutrons is we'll have to take 197, which is the mass number, and subtract out the number of protons that are there, and that'll give us the number of neutrons. So we take 197 minus 79, we get 118. So there are 118 neutrons in our element. All right, in this specific atom of gold. All right, so there's the number of protons, there's the number of electrons, and this is the number of neutrons. All right, now the next question is how many protons, neutrons, and electrons are in Au 197? Now notice that this 197 is the same 197 we have up here, and we've got the same element. They're both gold, so that tells us that it's exactly the same atom as the one above. So all of these values are going to be exactly the same. Notice that the mass numbers are the same and it's the same element. All right, so they're going to be the same value, 79, 79, and 118. All right, let's do a couple more. Protons, neutrons, and electrons are there in chlorine 35. So remember, this number here is our mass number. Okay. So first thing we need to do is come up with our atomic number. So we got to find chlorine on our periodic table. All right, so the number of protons is going to be equal to the atomic number. If we find chlorine, we'll see that it's in group 17. Remember, group, period. Okay, 17 is the atomic number, so that's just the number of protons. That's easy. All right, and then we find the number of electrons. Well, the number of electrons has to equal the number of protons. Okay, so that also has to be 17. And then finally, the number of neutrons is going to be equal to the mass number, which is 35, minus the number of protons, which is 17. And so we know that there are 18 neutrons in chlorine 35. All right. And then how many protons, neutrons are there in hydrogen? Now remember, in this notation, this number is the mass number, right? And this number here is the atomic number. All right, so the number of protons is equal to the atomic number, so hydrogen is 1. All right, the number of electrons is always equal to the number of protons, so that's 1. And so therefore, the number of neutrons has to be the mass number, which is 1, minus the number of protons, which is 1, and we get 0. So there are 0 neutrons in a normal, regular old hydrogen atom. Okay. Now, what we've essentially been looking at are what's called isotopes. Okay, isotopes are different versions of the same element. All right. Okay. Now, the reason they're the same element is because they have the same number of protons. Okay, so they have the same number of protons, but they have a different number of neutrons. Okay, different number of neutrons. So they're different versions. So they're still the same atom because we define, or they're the same element, and we define elements by how many protons they have. Okay, but they're different versions of it because they have a different number of neutrons. Okay. Now, isotopes are chemically alike because it's the number of electrons that determine chemical behavior. Remember, we talk about when we see this word chemical, remember we should be thinking about bonds. Okay, and we learned earlier that bonds are made by electrons. So because the number of electrons is the same, all isotopes are going to have the same chemical behavior. Now, next unit, or this unit, the second part of this unit, we're going to talk about nuclear chemistry. Nuclear chemistry, each isotope is going to have vastly different characteristics, but we'll get to that once we get there. All right. So for example, these are three different isotopes of hydrogen. We've got hydrogen, or protium, all right, and 99.985% of hydrogen atoms are just like that. So just like the last example we looked at, where it's just a one proton and one electron just kind of chilling in space. All right, now deuterium is H2, so this is where you have one proton and one neutron. Okay, one proton and one neutron. Okay, that's where, remember that 2 is our mass number, which is the number of protons plus the number of neutrons. And then this is called deuterium, and it's 0.015% of all hydrogen atoms are called deuterium. Okay, you might also see this represented, if you're so inclined, you might see this represented as a D for deuterium. And this is a very common analysis tool that analytical chemists use. All right. And then H3 is called tritium or tritium, and so this would be one proton, right, because it's still hydrogen, and then 2 neutrons. All right, but these things are so uncommon that they have negligible percentage. There are some floating around, and we can kind of make them sometimes by ramming elements into each other, but for the most part, tritium, it doesn't exist normally. Here's just a little graphic representing what they each look like. So this is hydrogen. The red bubbles, or the red balls here, are the protons, and the greens are the neutrons. So H1 has 1 proton, and H2 has 1 proton, 1 neutron, etc. And so then here's helium. We've got a helium 3 and helium 4, and then lithium 6 and lithium 7. All right. Now we got to figure out average atomic mass. So if you look at your periodic table and you look at the very bottom, okay, you'll see that there's a number, and that gives us the atomic mass, or the average atomic mass of the element. Now remember, when we talked about the mass number, we simply added the protons and neutrons together. Okay, now that's all good and fine, but the fact of the matter is, when we're dealing with chemicals, and we're mixing chemicals together and seeing their chemical behavior, really we have millions and millions and millions of these atoms that are all in there mixed together. So we can't just assume that they're all one isotope. Okay, so what we have to do is find their average atomic mass. Now, it's not as simple as just taking the three, we had the 3 hydrogens, and we had H1, H2, and H3. It's not as simple as taking those masses, adding them up, and dividing by 3, because remember, H1 was 99.985% abundant, whereas H3 was so little that it was negligible. All right, so we have to do what's called percent abundance. So it's a little bit more complicated way of calculating percentages, all right, or calculating the average atomic mass. All right, so to determine the average atomic mass, what we have to do is we have to take the mass of the element, or maybe a better word, mass of the isotope, okay, and multiply this by the percent, okay, and then we divide, and then we add them all together. So plus the next one, etc., etc. All right. So for this guy here, we're going to take B10. So this is our mass number. So we're going to take 10 times 20. All right. Plus 11 times 80. Okay. And now we have to think about this real quick. If we take 10 times 20. 10 times 20 plus 11 times 80, we're going to get a ridiculously big number. We know boron can't possibly be that big. Remember, when we find percentages mean, this symbol means it's been multiplied by 100. So we have to divide these guys by 100 when we multiply them, right? So we got to take 10 times 0.2 plus 11 times 0.8. Okay, and this tells us that we have an average atomic mass of boron of 10.8. Okay, we can double check our value by looking at the periodic table. The one I have pulled up says mass of boron, or the average atomic mass of boron, is 10.811. All right, which matches pretty close to what we found. All right, we'll do one more. Okay, I think there's one more on this slide. Yep. Okay, calculate the average atomic mass of the two isotopes of chlorine. Okay, so remember we're going to take the mass number, which is the 35 and the 37, multiply them by our percentages divided by 100. Okay, so if we take 35 times 0.7577, all right, and we're going to take 37 times 0.2423, all right, and then we're going to add these guys up. So 35 times 0.7577 is equal to 26.5195. Okay, so we'll just say 26.52, and then the other guy here is 37 times 0.2423. I got 8.97. Right, and we're going to add those guys together. I got 35.49. So based on this data, the average atomic mass of chlorine is 35.49. Okay, which is a little bit higher than what the periodic table says, but that's probably because we're only, dealing with two of the isotopes as opposed to multiple isotopes of chlorine. All right. So that's it. There's lots of practice for you to do, figuring out the number of protons, neutrons, and electrons, and average atomic mass. Let me do some practice, and let me know if you have any questions.